Hey everyone, so have you ever stared at a piece of recursive code and just thought, how in the world do I figure out how fast this thing runs? Well, if that's you, you're in exactly the right place. Today, we're going to pull back the curtain on the Master Theorem. Think of it as your secret weapon for analyzing divide and conquer algorithms.
Okay, take a look at this equation right here. This is what we call a recurrence relation. It's the kind of math you run into when you're looking at algorithms like merge sort. Now, you could bust out a recursion tree or try to solve this thing with substitution, but let's be honest, that's a ton of work and a real headache.
But what if I told you there's a much faster way? A simple little formula with 3 cases that can crack this thing in like under a minute. That's exactly what the Master Theorem does for us.
So here's our game plan. First, we'll quickly touch on why we even need a special tool for recursion. Then we'll get right into the Master Theorem itself and walk through its 3 main cases with some super clear examples. And to finish up, I'll give you a handy cheat sheet so you can have it all in one place. Ready? Let's do it.
All right, so what makes analyzing recursive code so tricky anyway? Well, it's because the cost of the function keeps calling itself just with smaller and smaller pieces of the problem. It creates this chain reaction that isn't so easy to add up.
To talk about this stuff like a pro, computer scientists use a special language called recurrence relations. Really, it's just an equation that describes the cost of a problem of size n by linking it to the cost of smaller versions of that same problem. It's basically the mathematical signature of any divide and conquer algorithm.
Now here's the catch. The Master Theorem is powerful, but it only works if the recurrence fits this exact format. Let's break it down real quick. A is just the number of times you call the function again. N over B tells you how much smaller the problem gets with each call. And that last part, f of n, that's all the other work you're doing, like splitting the problem up or sticking the results back together. For the theorem to work, this f of n part needs to look like a polynomial, and that's where our last 2 variables, k and p, come into play. Just think of k as the main power of n and p as the power on any log part.
And that brings us to the main event. The Master Theorem isn't some kind of magic. It's just a really clever 3-step process. All it's doing is comparing the work from the recursive calls to the work you do to combine them.
And here's the entire playbook. Step 1, you look at your equation and you just pull out those 4 variables, a, b, k, and p. Step 2, you calculate this one value, log base b of a, and you compare it to k. This comparison, this is the absolute heart of the theorem. And finally, step 3, based on whether that log value is bigger, smaller, or the same as k, you just apply the rule for that case. That's it.
So, let's jump into case 1. This is what happens when the work of breaking the problem down and solving all the little pieces is way bigger than the work it takes to put them back together. The recursion itself is the dominant part. So here's the rule. If that value you calculated, log base b of a, is strictly greater than k, then the time complexity is simply theta of n raised to the power of that log value. The f of n part? It's just too small to matter in the long run. Let's go back to that first example we saw. T of n equals 8t of n over 2 plus n squared. So our a is 8, our b is 2, and since f of n is n squared, our k is 2. There's no log factor, so p is just 0. First thing we do is calculate log base 2 of 8, which is 3. Now we compare that 3 to our k, which is 2. And as you can see, 3 is definitely bigger than 2. Boom! That puts us right into case 1. The result is just theta of n raised to that log value we found. So it's theta of n cubed. See how easy that was? No crazy recursion tree needed.
Okay, but what happens if the work is, perfectly balanced? That's what brings us to case 2. This is where the work done in the recursion is pretty much the same as the work done combining everything at the end. When you get a tie like this, we have to look at our other variable p to break it. As you can see in the table, the final answer depends on whether p is bigger than, equal to, or less than -1. So we just have to be a little careful and apply the right subrule. Here's a super famous example. T of n equals 2t of n over 2 plus n. If you've studied algorithms, you might recognize this as merge sort. Our a is 2, b is 2, and k is 1. Notice there's no log term, so p is 0. Okay, let's do the math. Log base 2 of 2 is 1. We compare that to k, which is also 1. It's a tie. So because they're equal, we now have to check our p-value. Remember, p was 0, and 0 is greater than -1. That means we use the very first subrule for case 2. The complexity is theta of n to the k, but we multiply it by log n. This gives us the famous answer for merge sort, theta of n log n. And that brings us to our last stop, case 3. This is pretty much the exact opposite of case 1. In this situation, the work you do to split the problem and combine the results, that f of n term, is the real heavyweight. It's the bottleneck that dominates everything.
When k wins the big comparison, the answer is basically just determined by that f of n term. We just have to check our p-value one last time. If p is 0 or positive, the answer is literally just theta of f of n. If p is negative, we drop the log part, and the answer is theta of n to the k.
Let's check out this example. T of n equals 2t of n over 2 plus n cubed. Okay, a is 2, b is 2. Since f of n is n cubed, our k is 3, and our p is 0. So we calculate log base 2 of 2, which is 1, and we compare that to our k value of 3.
Well, 1 is obviously less than 3, which throws us straight into case 3. We quickly check m, which is 0. This means we use that first subrule, and our answer is simply theta of f of n. In this case, that's theta of n cubed. Simple as that.
All right, we've made it through all 3 cases. Now, to make sure this all sticks in your brain, let's put it all together in one single beautiful cheat sheet. You are definitely going to want to screenshot this one for your notes.
And there it is, the whole thing in a nutshell. Case 1 is when the recursion is king. Case 2 is when it's a dead heat. And case 3 is when that combination work wins out. See those little asterisks for cases 2 and 3? That's just our little reminder that for those, you have to remember to check the value of p to get your final answer.
Okay, before you go, just a few super important reminders, especially if you have exams coming up. 1. Always start by identifying your 4 variables. 2. The whole game is that one comparison, log base b of a versus k. 3. Remember p is your tiebreaker for cases 2 and 3. And 4, this is a big one, know its limits. This theorem is amazing, but it only works for occurrences in that very specific at of n on b plus f of n format.
So, let's wrap up with a quick challenge to test out your new skills. We already did this one, but can you solve it from memory right now using our 3-step process? What's the time complexity of merge sort? Think it through. You now have the perfect tool to figure it out in just a few seconds.